how you determine the roll center of your suspension geometry. So you take the upper arm and the lower arm, you find the instant center of the right wheel, and then you take the instant center of the left wheel, and then you take and you draw the line from those instant centers. The intersection between the yellow lines are not the lower ball joint. It's drawn as if it's like that, but it's not. Okay? Many times the instant center is actually here, not here. And then you draw a line from that instant center to the tire contact and opposite, and here is your roll center. Usually your roll center will be slightly off the ground, okay? Because otherwise you'll be too much body roll. So that's your roll center. The distance between that determines your roll. Between the center of gravity and the roll center. Okay, so now, why? Okay, that's the pitch center. Okay. So the question, my question to you, why not make the roll center all the way up there, close to the center of gravity?
The curve should be higher. The curve. And the rotating point also will be higher, so the car will roll more.
No, there is no body roll if you are in line with the center of gravity. So there's actually something else going on. Okay, it's called jacking. So the concept of jacking is that what happens is that cannot find the diagram. Okay, so if this is your roll center, this is your left, this is your right, and this is your roll center, this is the ground. Okay, because of this roll center, remember that there is a sideways force when you turn, right? So there is this side force. Now, the side force will have to rotate this, and so as a result, you got the net vertical force on this roll center. And what's going to happen is called jacking. This is called the jacking force. If you got your roll center too far up, the jacking force will be significant. And this jacking force will actually lift your car. And it will lose the grip. So if your roll center is too high, you're actually lifting the car up. And especially on the outer side, it'll be really negative, right? So you'll actually lift the car. So you don't want that to happen too much. So in the end, what's your solution? Well, the solution is make your center of gravity lower. So that's why, because your roll center cannot be all the way up. If you want less roll, then you're going to have to lower the CG closer. Okay? And that's why people lower their car. But if you lower your car too much, you're also in danger of bottoming of your, because you have a shorter spring, so this can bottom out also, right? If it bottoms out. The jacking, by the way, also helps bottoming out. So if your suspension bottom out too much, increasing the roll center will actually help not bottoming out because it actually lifts your car. So it reduces the displacement that you are under. Okay, now finally, where's the dive? Okay. Notice also your McPherson will always be like this. The shock absorber will be always have a positive caster like that. Okay, so there are always some rotation when the hub goes up. This is called the pitch and roll center. So this is the blue dot is where the car rotates during dive or squat. So that's determined by the angles of the control arms. Look at how it's slightly angled this way. It's also slightly angled this way, following the caster. So you take those yellow lines and another yellow lines, and you'll find the pitch center. Okay? So the pitch center can also be tuned depending how you angle the upper control arms. So you see, suspension geometry is not that simple, right? So you can tune the length of your upper control arms also to control the camber controls. So in short, the double wishbone is superior because you'll maintain better contact during roll. But McPherson, you are stuck with this rotation in many ways. Okay, you're trying to control it, but there's only so much degree of freedom you have. But hey, it's very simple. I think he has a good explanation here.
Moving the numbers to the front, and here's what it looks like. And this is going to have three attachment points to the chassis, so two attachments.
Let's hear his explanation on this.
The shorter you make the control arms, the wheel will move up and down more in an arc, which is not that good. But in production cars, they don't have that much space to make these control arms that big. So that's why they will often compromise on the design, and they will bend the control arms or shape them in a way so they can fit them in an actual car. So they don't make the best of the double wishbone configuration, but it still is a lot better than some of the other suspensions out there. So now talking about the other really common suspension found in cars these days, that's going to be the McPherson strut. And almost every other production car is going to use this suspension in the front because it is really cheap to implement in cars. And what it basically is it's going to have the same lower control arm design as a double wishbone suspension, but the upper control arm is replaced by bolting the knuckles straight to the strut. And here's what it moves like. And this suspension is going to have three attachment points to the chassis, so first we straight to the knuckle, saves the ball joint up and the ball joint on the lower control arm. And the roll center and pitch center in this suspension are measured by drawing a line perpendicular to the mounting point on the top strut. Because and arm really starts to lead strut, and then it will start to angle the lower part of the wheel backwards too. So the wheel gains camber to a certain extent, and then after that it starts losing camber again. So you never get as much camber gain with a strut type suspension as you do with the double wishbone suspension. And to increase the camber gain on this suspension, you can do that by changing the angle of the strut. But the problem with that is that when you change the angle of the strut, you're changing the kingpin inclination at the same time. Because the steering axis in this suspension is determined by where the top of the strut is mounted.
So that's the dilemma, right? You're changing the SAI also. Okay. Enough about suspension geometry. Any questions? Okay. You want to look up what your suspension design is for your car, go ahead and maybe do a little bit of Googling. The pictures and identifying your design. So, what's your car's suspension design like?
McPherson.
McPherson. At the rear?
Well, I don't know.
What's most common is basically what is called a trailing arm suspension. It's kind of a McPherson with an additional track bar. What about yours? McPherson also?
McPherson front, torsion beam rear.
Yeah. What's yours?
Inverted McPherson.
How is that?
Instead of having the oil pressure down and the piston going
Oh,
down.
the
oil is up and then
shock absorber is upside down. Wow, I never knew that. How is that?
Evo 10.
Hmm.
Yeah.
What's the advantage of that?
So it says, by putting the shock absorber upside down, the larger and stiffer outer tube handle the side loading force. This reduces the flex during hot cornering,
Oh,
keeping the outer alignment more consistent.
inverted McPherson.
First.
Is it on the Evo?
Yes, Evo 10.
Is that how it's like? Maybe. Never seen something like that.
They have it on Google.
Oh, Google, okay. Come on. Just search here.
The inside.
This one?
Yeah. So the damper is inverse.
But how will that increase the stiffness?
Because the bar for the piston is upside down. So yes,
So,
instead of the bar being up, it's down.
okay. I wonder why other cars will do that. Very interesting. Okay.
I think it's only on the Evo 10.
Only on the Eagle 10.
Yeah.
Alright. Okay. What else do you find? What yours?
Only the front is different. Rear is
Torsion bar.
multiple links.
Oh, multi-links. Okay, double wishbone. Alright. Okay, let's go over shock absorbers. Here's a good overview of the different types out there.
Think of horsepower or the cubic capacity of an engine. But all the power delivered to the powertrain can be wasted if not handled by an efficient suspension system. The shock absorber, also known as a damper, plays a vital role in the suspension system, not just for providing better comfort, but it also ensures consistent traction to the road surface, better steering stability, and also improves handling of the vehicle. Technically briefing, a shock absorber is nothing but a hydraulic pump which absorbs the kinetic energy of the suspension system and dissipates it into the atmosphere as heat. Shock absorbers found in most vehicles can be strut type or conventional telescopic type, although the operating principles of both are almost the same. In this presentation, we're going to take a look at the strut type shock absorber, mostly found in the front suspension of an automobile. A strut-type shock absorber is mounted between the body and the steering knuckle. With the steering knuckle connected to the lower arm, the system constrains the wheel displacement only to be in the vertical direction. The steering knuckle is designed in such a manner that the wheel can be turned within the limited range by the steering rack assembly. A strut assembly comprises a shock absorber, coilover spring, top strut mount, and a dust boot over the piston rod to prevent any contamination to the oil seals. Despite the popular belief, it's the coilover that does take the weight of the vehicle and not the shock absorber. The strut housing includes a piston rod, which moves up and down, a rebound stopper, a piston valve unit, a base valve unit, and the hydraulic fluid. The shock absorber is designed to have a working chamber and a reserve chamber. The hydraulic fluid transfer between these chambers is controlled by the base compression valve.
This is called the twin tube design. There's also monotube design.
Such a configuration using two chambers is known as a twin tube shock absorber.
Now, you see that this oil can leak if your main shaft is scratched or the seal is broken. And that's usually how shock absorbers are out. and needs replacement. Or you can refurbish it, but I don't think it'll last that long if you refurbish it. You ever refurbish a shock? No.
Not recommended.
I don't think it's worth the effort. I mean, people do that.
Though other variants, such as the monotube shock absorber, which uses a single chamber, are also present in the industry. For the shock absorber to provide its optimum performance, the working chamber must be full of fluid at all times. The purpose of the reserve chamber is to ensure that the working chamber is filled with fluid, regardless of how compressed the piston is. Thus, the reserve chamber will always be partially filled. The system is added with liquid nitrogen while manufacturing, which expands and acts as a compressed gas on the remaining volume of the reserve chamber. The calibrated valve at the base controls the resistance experienced by the piston during the compression phase, while the fluid flows almost freely from base to top through the piston valve. As the piston moves towards the base, the compression valve opens in a controlled manner, allowing the excess fluid to flow to the reserve chamber.
Why oil?
It's not compressible.
Okay, it's incompressible. Are you familiar with what is called a Newtonian fluid?
Yeah.
Okay. What is the definition of Newtonian fluid?
Newtonian. When you like punch it hard, it doesn't like goes through. But when you like softly, it will.
So in other words, the stiffness of this fluid depends not on the displacement, like springs, but on velocity. So the faster you're trying to change this fluid, the stiffer it acts. Okay? And it's because Newtonian fluids are basically, if you take like a cube of this element or material, you're basically trying to make the square into a diamond, and this is called shearing. And Newtonian fluids behave this way, and if you go into the fluid mechanics, it basically is shearing the fluid, and the fluid acts harder when you displace it fast. And so this is the effect that we want, because on small bumps, I want it to be soft. But on hard bumps, I want it to immediately stop it, right? Otherwise, you'll bottom out. So this is why hydraulic fluids are used. And you just pass it through this small valve and you'll have that effect.
During the rebound phase, the piston rod tries to restore its position against the compressive energy, and the rebound valve ensures this happens in a controlled manner.
And it becomes hot, by the way.
As a result, the previously displaced fluid to the reserve chamber is pulled back to the working chamber. The repeating action absorbs the energy from the suspension system and transfers its heat to the atmosphere. With the pressurized gas added into the reserve chamber, the system avoids the phenomenon of generating air bubbles in the fluid, known as cavitation or foaming. Damage to the oil seal can cause fluid leaks, resulting in foaming and inconsistent shock absorber performance. Shock absorbers can usually last up to several thousand miles, but they do get defective over time due to the millions of operation cycles they have to endure. Defective shock absorbers could cause the steering system to rattle, change shock movements,
Oil seals, maybe.
drive up shock performance of the suspension system.
Okay. Now, all of these are all passive shocks, right? And here's where the revolution happens, is what if you can make this active? And what if you can literally control? And I love this video on the one. Okay, it's a bit long, but I think
Try to have an honest conversation about the state of the automotive industry in 2026 We must start by dismantling a lie that has persisted for exactly 140 years. Since the very first internal combustion vehicles rolled out of sheds in Germany, the fundamental interface between the machine and the road has remained primitive. We have been sold the idea of advancement by brands like Mercedes-Benz, Bentley, and Rolls-Royce. They use seductive marketing terms like magic body control or active ride. But if you strip away the leather, the wood, and the soundproofing, and look at the raw mechanical engineering, you find a system that is functionally identical to a Victorian horse-drawn carriage. We rely on a passive system, a steel spring to bear the weight of the vehicle, and a tube filled with oil, the damper, to stop that spring from oscillating indefinitely. This system is, by definition, a compromise built upon a failure. It relies on the principle of reaction. The wheel must first hit an imperfection in the road surface. It must be forced upwards violently, and only then does the damper attempt to mitigate that energy by forcing hydraulic fluid through tiny, restrictive valves.
So that is the physics limitation, right? I mean, you just cannot go around it. You know there is a bump on the road after the bump happens, and so you can only react to that bump.
This creates a fundamental physics problem known as hysteresis. No matter how fast the processor in a modern Porsche Panamera is, the oil in the damper has physical viscosity. It takes time to move. It takes time to build pressure. There is a physical lag, a latency, between the road impact and the suspension's reaction. For a century, engineers have gaslighted us. They told us that this lag is unavoidable. They told us that the trade-off between ride comfort and handling precision is an immutable law of physics. They told us you cannot have a car that handles like a Formula One racer and rides like a hovercraft. They lied. The truth is that the solution to this problem was identified decades ago. We must look back to the early 1990s. The Williams Formula One team developed the FW14B, a car with active hydraulic suspension that was so dominant it was banned by the FIA for being too effective. It proved that if you control the ride height actively, you gain massive aerodynamic advantages. Simultaneously, Dr. Amar Bose, the genius behind Bose Audio, spent 30 years and hundreds of millions of dollars proving that electromagnetic motors could replace dampers entirely. His Project Sound, Lexus prototypes could jump over obstacles and corner with zero body roll. But the car industry killed the project. They claimed it was too heavy, too complex, and crucially, it consumed too much power. The giants of Germany and Detroit looked at the future, shrugged, and returned to polishing their antique hydraulic valves. They chose evolution instead of revolution. They bet that the internal combustion engine and the 12-volt electrical system would rule forever. They were wrong. They failed to predict the rise of the high-voltage electric vehicle platform, which would finally provide the immense energy source required to make the impossible D-Young suspension a reality.
So, the revolution happens when you got a high-voltage battery, because then you got the power. I mean, you got enough energy to accelerate the car. You got enough energy to race the car, right? So, and you got a high-voltage system, and so you can have very powerful motors.
This brings us to the technological rupture we are witnessing today. BYD, a company that began by making mobile phone batteries in Shenzhen, has effectively picked up the baton that Western engineering dropped. With the Yangwang U7 and the Disu Z system, they have mass-produced the linear motor suspension. But we must be surgically precise about what this is.
You're basically riding on motors. No springs, no dampers.
This is not air suspension. Air suspension is just a rubber balloon replacing a steel spring. It is still governed by the slow movement of gas. The Disu-Z eliminates the fluid and the gas entirely. It is a dry system. At each corner of the car, there is a three-phase linear electromagnetic motor. Imagine a high-speed maglev train wrapped into a compact cylinder inside the wheel arch. When you apply electrical current, It generates force, not pressure, but force. And it does so at the speed of light. The critical number that defines this revolution is 10 milliseconds. That is the system's reaction time. To put that in perspective, the human brain takes approximately 200 to 250 milliseconds to process a visual threat. A blink of an eye takes 100 milliseconds. The Dessau Z is reading the road via LiDAR and sensors, calculating the force vector, and physically moving the wheel 20 times faster than you can perceive that a bump exists. This allows for the application of skyhook theory.
So the other revolution that enables this technology is LiDAR and chip microprocessing. Very powerful microprocessors. It didn't exist 10 years ago, 20 years ago. So, I mean, the processor here is like multiple times faster than my computer 5 years ago. It's crazy. And it's cheap, relatively speaking.
In the real world, the car body remains fixed in space, perfectly level relative to the horizon, while the wheels articulate furiously underneath, mechanically disconnected from the chassis. The motor can extend the wheel into a pothole and retract it before the shockwave has time to transfer to the cabin. It effectively erases the topography of the road. Furthermore, we must address the unsprung mass myth. For decades, critics and purists argued that bolting heavy electric motors to the wheels would ruin handling, as heavy wheels carry too much inertia. This is true for passive systems, but the Dessau Z is active. The motor is powerful enough to manage its own mass. It can accelerate the wheel downwards at speeds greater than gravity, 9.81 taman-mas-2, forcing the tire into the tarmac to generate mechanical grip where none existed. It turns the suspension from a shock absorber into a downforce generator, or it creates a level of connection to the road that no mechanical spring, no matter how expensive or well-tuned, can replicate.
If you get a flat tire,
If the
it can
U7
lift
represents the
one
luxury
wheel.
application of this technology. The Yangwang U9 represents the weaponized application. This car features the Daisus X system, the most extreme iteration of the technology. This is where we see the true potential of the 800-volt silicon carbide architecture. The suspension system on the U9 has a peak power output of 36 kilowatts. Think about that for a second. The suspension alone uses more power than the entire drivetrain of a small city car. Why? Because to defy gravity, you need brute force. The viral footage of the U9 jumping off the ground is not a carnival trick. It is a demonstration of power density. For a 2.5-ton vehicle to leave the Earth, the motors must deploy explosive force instantly. But the real revolution is not the jump. It is the safety capability. The U9 allows for three-wheel drive. In a traditional supercar, a Ferrari, a McLaren, or a Lamborghini, if a wheel disintegrates at 120 mph, the suspension collapses. The chassis grinds the asphalt. The friction causes a violent spin, and the result is often fatal. The U9 is different. Its sensors detect the loss of vertical pressure in milliseconds. The Dessau X system instantly retracts the hub of the missing wheel, lifting it clear of the ground. It then stiffens the diagonally opposite corner to act as a fulcrum and uses the quad motor powertrain to torque vector the car straight. It turns a catastrophic mechanical failure into a manageable event.
So if you got a flat tire on one of them, it can lift that like lifting a leg. Man, that's unthinkable. And then it corrects the torque vector by energizing certain wheels certain ways. I mean, I have to say that I'm impressed.
This is the ultimate redundancy. It proves that the analog feel of European supercars is actually just a lack of active safety systems. The comparison with European rivals is brutal. The Porsche Panamera uses a 48-volt active anti-roll system. It is good. It can twist a bar to stop roll, but it cannot lift the car. It cannot jump. It cannot drive on 3 wheels. The 48-volt system is a toy compared to the 800-volt sledgehammer of the DSUS X. BYD has brought a nuclear weapon to a knife fight, and the legacy manufacturers don't even realize they are dead yet. And the Yangwang U8. We cannot ignore the third pillar of this ecosystem, the DSSP found in the Yangwang U8. While the Z and X systems use linear motors for speed, the P system uses hydraulics for immense power and travel. This system rivals the best off-roaders from Land Rover and Toyota, but functionally destroys them. It is the world's first intelligent hydraulic body control system with concurrent 3-axis control. It does not use mechanical anti-roll bars. Instead, it links the hydraulic chambers across the axle on the road. Valves close to stiffen the car by 200%, eliminating the wallowing of a heavy SUV. Off-road, they open to allow 150 millimeters of independent articulation. The genius here is utility. The pumps are so powerful that the U8 can perform emergency float mode. If the car enters deep water, it seals the body, shuts the intake vents, raises the suspension to the maximum to reduce drag, and uses the spinning wheels to propel itself like a boat. It can turn on its own axis, tank turn, because the suspension stabilizes the chassis, while the motors spin in opposite directions. Even more practically, if you get a flat tire in the desert, the suspension can lift the damaged wheel high enough to change it without a jack. The car lifts its own leg like a dog. This is not just luxury. This is survival engineering. We must also look at the thermodynamics of this revolution. For a century, suspension has been a parasitic system. A traditional damper takes the kinetic energy of the car's vertical movement and wastes it as heat. It warms up the oil and dissipates that energy into the atmosphere. The DSUS and X systems are fundamentally different. They are generators, because they consist of magnets moving through coils. Every bump in the road induces an electrical current. On a rough surface, the suspension is actively harvesting energy and feeding it back into the high-voltage battery. This is regenerative damping. While it will not recharge the car fully like a charging station, it offsets the power consumption of the system. It turns the roughness of the infrastructure into electric range. This closes the energy loop and solves the efficiency problem that killed the original Bose project in the 90s.
So the reason this cannot work in the old prototype is that it was not, there is no battery to charge, right? Now the other, people know regenerative damping for a long time, but the problem is they do not have a motor and generator in one set. So it'll be ridiculous to have a passive system and a generator at the same time. It just doesn't make sense. Now, since your suspension is a motor anyway, just flip the switch and recover the battery, the electricity.
The car becomes symbiotic with the road surface. The worse the road, the more energy the suspension recovers. This is a level of efficiency integration that internal combustion vehicles could never achieve. And the software era culturally, this marks the death of the chassis tuning guru. For generations, brands like Lotus, BMW M, and Porsche relied on master engineers to test thousands of springs, shims, and bushings to find the perfect soul of the car. It was a black art. The DSUS system renders this obsolete. The feel of the car is now just code. The stiffness, the rebound, the roll stiffness. It is all defined by software variables. This means the car can be updated over the air, OTA. You can download a track mode that mimics the stiffness of a GT3 car, or a Campinas comfort mode that mimics the float of a 1970s Cadillac. The hardware is identical. The personality is a download. The soul of the machine has migrated from the metal to the silicon. This allows BYD to iterate the handling of the car every month based on user data, something a mechanical suspension can never do.
It's all software, guys. Crazy. And then later it'll be AI. So yeah, I love this video. I think it's revolutionary. There are other coverage on that car. Anyways, so let's close with a little bit conversation on steering. I mean, steering is not that complex, but
To drive, the most difficult control to master.
I'll just mute the video. So, steering. When you want to steer, you cannot turn the left and front wheel the same, right? What is that called? Begins with an A. Ackerman steering, right? So you have to rotate at different angle to actually follow the path without wear, even though there are some exceptions called anti-Ackerman. But that's the yeah. So, what is the Ackerman angle? The Ackerman angle is, you have to imagine an instant center or a point of rotation of the car there. Okay? So you have to take the rear axle, and then they have to all intersect at the line in order to create this smooth turning, right? And that results in a different angle between the front two wheels. Okay? Okay, I think it's clear enough for you guys. So how do you achieve this? Well, you achieve it using a certain angle on the position. And usually there is not an additional arm, it's just the hub shaped in a certain way. So if you look at the hub from the top, okay, so often it's like that, and this is where the tie rod attaches. If you take that center to the back, you will have to intersect the rear axle. Okay, so the angle of that blue line intersects at the rear axle. This is the rack and pinion. I think that's pretty self-explanatory. So this arm is usually not an arm. Usually it's integrated as the hub shape. So that's the tie rod. You got the inner, you got the outer. The inner tie rod has a ball joint here too. So there is a ball joint here, there is a ball joint there, because suspension, right, going up and down, and there is some front and back motion too. Okay, so that's the animation. The mechanism, the angle creates that change. So the intersection of the front two wheels have to intersect the rear axle line. That's how you create steering without excessive wear. And the steering column also have that double U joint. Okay? Now they have to be in phase in order to remove the velocity fluctuations you look up. Okay? This is the power steering. There are two types. There is one on the rack and there is also one on the column. The one on the column has a planetary gearing. So
The motor is capable of rotating in both clockwise and anti-clockwise directions. An electronic control unit decides the amount of power the motor should transfer to the column. The ECU takes the following inputs, such as the torque the driver has applied to the steering wheel, the steering angle, the steering wheel's speed, and the vehicle speed.
now let me ask you one thing to brainstorm a bit. How will the motor knows how much torque to apply?
There's a sensor on the column. that,
What type of sensor?
I think it's pressure. It's twisting.
What
torque.
does it measure? Does it measure the twist angle? The pressure? What does it measure? Exactly.
The force applied.
Why the force? Why not the displacement?
Displacement can be related to just the velocity, but like force is the amount of pressure, I guess, you apply.
If you measure the angle, then you are rotating the wheel anyway, right? So there is no information there. But if you measure the twist torque, you are measuring how much assistance do I need, right? How much assistance do I need? And that's what the power steering's job is.
And then decides the appropriate torque to be supplied. A Hall effect-based sensor and torsion bar arrangement is used to measure the driver's torque input. Due to the motor's power assistance, the steering wheel rotation becomes effortless for the driver. Do you think this is a perfect mechanism? Wait for a moment and think about what happens to the steering in the case of a motor failing. You might be aware of the fact that a worm screw can turn a worm gear, but a worm gear cannot turn a worm screw. This means that if the motor fails, any manual rotation by the driver will be blocked by this constraint of the worm drive. In short, the steering becomes jammed. To overcome this issue, the rotation from the steering wheel is never directly connected to the worm gear. Instead, it passes through a planetary gear set. Here, the driver's rotation is given to the sun gear. The output is drawn from the carrier, and the worm gear also becomes ring gear of the planetary gear set.
So if the ring gear is fixed, you can still rotate between the ring and the planet carrier, but the ring can also help your torque at the same time simultaneously. But I've seen many EPS actually act on the rack itself rather than on the column. This is an old power steering with hydraulics. I do not discuss it because it's getting less and less common. It's a purely mechanical system. That's what's nice about it. What you control here is basically the twisting of the shaft will create the valve opening. And the valve opening will channel the pressure depending whether you need it here or here. So it's simultaneous at the same time. So that's how the hydraulic, but you need pump, and the pump can leak. The hydraulic here will leak, and that's not good. So that's the hydraulic systems. Finally, there is steer-by-wire.
The driver by reducing the effort needed to steer. It still relies on a physical and mechanical connection between the steering and the wheels. In contrast, steer-by-wire relies entirely on electronic signals. There's no mechanical fallback unless a backup system is designed in. A vehicle equipped with a steer-by-wire system can be manually controlled by a driver using a steering wheel, which is electronically connected by an ECU. Instead of a traditional mechanical steering column, the rotation of the steering wheel is detected by sensors that measure steering angle and speed. The ECU interpret the driver's input and send electronic commands to steering actuators, which physically turn the wheels side to side, thereby steering the vehicle. The safety of these systems is often ensured through redundancy, which may include multiple input sensors, dual or triple, redundant communication networks and power supplies, and redundant steering actuators per wheel. These redundancies enable the system to maintain functionality even if one component failed, a design principle known as fail operational. In some advanced systems, if steering actuators fail on one or more wheels, the vehicle may be able to partially compensate by using techniques, such as torque vectoring or brake-based yaw control on the remaining operational wheels. However, this compensation typically supports limited emergency control rather than full steering functionality.
I don't know, man. It's a bit too scary for me. I like the mechanical connection still. They do have redundant systems. I don't know. Still, I think the advantage is too little. I think is what I'm saying. What do you think are the advantages of steer-by-wire? Why would they do that?
Fast response.
This moving part.
You can manipulate the response. I mean, fast response can be electrically assisted, but you can have a variable ratio. So you can have a small ratio, and then at a certain angle, so it becomes like an F1 steering wheel without the rotation, right? You can vary that, but I don't know. Is that nice? Is that an advantage? Others cite the space you get from having no shaft. So you got more leg space. Still, others also say it's the safety because during major crash, then the steering column will push against you. I don't know. I'm not ready for it. There are some cars, Cybertruck has it.
Yeah.
Yeah. All right, well, that's it for today, guys.